Hello everyone, my name is Sravya. So I'll be talking about image transformations in today's video lecture. So why do we require image transformations? How do we perform the image transformations in detail using mathematical equations? We will talk about today. First thing, why do we require image transformations? We all know that most of the image operations they can be performed in spatial domain as well as in frequency domain. So what actually is spatial domain and what actually is the frequency domain? When we are talking in terms of pixels, when we are talking in terms of pixels, x and y positions representing the pixels using x and y's, then we are referring it to be spatial domain. Then when we are doing frequency transformation techniques, then the representation of our image will be given in the frequency domain. So how is this image represented in frequency domain? We will see in our later of our video. So till now, whatever the pixel manipulation operations like histogram, intensity transformations we have talked about, they are all performed in spatial domain. Why do we use spatial domain? Because they can be easily visualized, right? They can be easily visualized using histogram, intensity transformation functions, coordinate systems. So most of the time for easy visualization we use spatial domain. However, why we require frequency domain manipulations? Because when we do manipulations in frequency domain, it is easy to solve complex problems and and it is faster to compute. So when we are trying to do manipulations using computers, writing a lengthy program, then using frequency domain manipulations for the image processing is very useful. So what is the image transformation? Image transformation is representing the image using frequency components. So what are the frequency components? They are the intensity values. Intensity values which are transformed into our frequency domain, right? So when we are transforming our intensity values into frequency domain representation, so such a representation of the image is called as image transformation. So in other terms, we can also say that the spatial as well as the frequency domain are two ways by which same information in the sense the same image is represented in different ways. So what we have right now is image data which is in spatial domain. Using mathematical transforms, we are converting into a frequency component that is in frequency domain. Then using the inverse transforms, we are converting back from the frequency domain to spatial domain. So the combination of the mathematical transforms plus the inverse transforms are called as the transform pairs. So we will be talking about what are the mathematical transformation formulas, what is the inverse transform formulas, and how are they different, what are the different ways by which the mathematical transforms are existing for each transformation technique, what are the specific inverse transformations and what are the limitations in our class. Yes. So what are the types of the image transformations that are existing? First one is orthogonal and then next is non-sinusoidal signal. So what do you mean by orthogonal and non-sinusoidal signal? We say that orthogonal image we call it as orthogonal image transformation technique if the basis functions are of sinusoidal in nature. So, if their basis functions are of mathematically, we can write them as sine functions, cosine functions. Then we call it them as orthogonal basis functions, which are for example, the transformation techniques that we will be talking about are Fourier transform, discrete Fourier transform. So FTS, Fourier transform. When we come up to DFT, we call it as discrete Fourier transform. Right? Now, when we come about to non-sinusoidal signals, what do we call them as? If the basis functions are non-sinusoidal signals. Basis functions are non-sinusoidal signals, then we call it as non-sinusoidal transform technique. We call them as non-sinusoidal transform techniques. For example, we have Haar, we have Walsh-Hadamard, KL transform, slant transform techniques. So, all these transformation techniques we will be talking about. So, the transformation techniques that we will be talking about are Fourier transform, discrete Fourier transform, Haar, Walsh-Hadamard, KL, and slant. So these are the important image transformation techniques that we will be talking about in our lecture. Yeah. So what do these image transformation do? Represent the image using series summation of set of unitary matrices. So what is the unitary matrix? Why do we have to represent as a series summation of set of unitary matrices? That we will see now. So we all know that a unitary matrix is A. If we say a unit matrix A is unitary matrix, then we can say that A inverse is equal to the complex conjugate transform of the complex conjugate of the same matrix. If this equation is satisfied, then we call it as a unitary matrix. So, unitary matrices are very important in our image transformation techniques, right? So, before we go to further details of what is orthogonal, what is orthonormal signal, let's consider for now that I have a function x of t which is represented by this waveform. Okay, so using the orthogonal signal technique, then we can say that x of t, let it be any random signal. Let it be any random signal. We say that x of t can be represented by a sum of set of orthogonal basis functions. We can say that if x of t is a random signal, then x of t can be represented by sum of set of orthogonal basis functions. So, what are orthogonal basis functions? For example, we will consider if a of n of t is a set of functions, say a naught of t, a1 of t, a2 of t, a3 of t, so on and so forth, an of t. Okay, let me represent it by a of t here. Okay, now I will call all these waveforms, all of these signals are defined between the time period 0 t naught plus 0 to t. Okay, I will call a naught of t and a1 of t as orthogonal if and only if integration over if the integration t naught plus t of a naught of t n of t dt is equal to k if m not equal to n and it is 0. Okay, so if I consider two functions a naught and a1 am, I consider two functions am of t and an of t, then I will say that am of t and an of t are orthogonal signals if and only if I am multiplying these two signals am of t and an of t and integrating over the time period t naught plus t naught plus t. Then if the value is equal to 0, if m is not equal to n, and if it is k, if m equal to n, then we call them as orthogonal signals. Okay, so orthogonal signals are if they satisfy this equation t naught integration t naught plus t naught plus t am of t into an of t dt is equal to k if m equal to n, 0 if m is not equal to n. Okay, now if this constant k value is equal to 1, then I call it as orthonormal signal functions, right? So I am saying that if x of t is a random function, I can represent it by a sum offset of orthogonal basis function. Orthogonal basis functions will satisfy this equation, saying that if am of t into an of t is equal to k, then for m is not equal to n, m equal to n, and 0 if m is not equal to n, right? If k equal to 1, we call them as orthonormal functions. To understand better what is orthogonal signals and what is orthonormal signals, we will just consider a example. We will consider an example as, say, suppose a the set of vectors are sine of omega t, sine of 2 omega t, sine of 3 omega t. Assume, just consider this example where a of t is sine of omega t, sine of t 2 omega t, and this, and it is defined for a time period 0 to t. Now, if I consider whether these two functions are orthogonal or not, then what we have to do? We have to calculate sine omega t into sine 2 omega t, right? So before I calculate, I will calculate it using graphical representations. So if I represent this is t, then this is sine omega t. Now how do I represent my sine 2 omega t? I can represent my sine 2 omega t as this. So this will give me my sine 2 omega t. Now, if I am trying to multiply these two equations, I get the graph as this part. For this part, both the values are positive, so I get a positive waveform. Here I have my positive, which is multiplied by negative values. So I'll get my negative waveform. In the next part, similarly, I have a negative values multiplied by my positive value. So I'll get my negative waveform. And the next part, both are negative. So I get my positive waveform. Right? So this is the value of sine omega t into sine 2 omega t waveform. We all know that if I want to calculate the integration over the time period 0 to t of a function is equal to the area enclosed by that waveform in the time period. So from this waveform we can observe that the values are 0. Since the integration of 0 to t for the time period sine omega t into sine 2 omega t dt is equal to 0, we can say that sine omega t and sine 2 omega t are orthogonal signals. We can say them, they are orthogonal signals. So similarly, sine omega t, sine 3 omega 3, sine 2 omega t, sine 3 omega, sine 3 omega t. These two are also pairs of the orthogonal signals. Right? Now, let's assume that x of t is one function. Since I can represent it as a summation of set of orthogonal signals, I am representing it as summation. Orthogonal functions which I am considering are orthogonal basis functions are considered as an of t into cn of t, where n is ranging from 0 to infinity. So this is the function where x of t is represented by summation of the basis function which are orthogonal. So this is called as the coefficients. So if we consider this is the set of orthogonal function and Cn is the nth coefficient. Right? So if I have u as my set of samples or u as the set of my discrete samples, from my previous slide, I can see that x of t is equal to summation of Cn an of t. Right? Now, if I observe here, I can say that integration x of t dt is equal to integration of t sigma Cn an of t into am of t dt. I am multiplying both sides a function which is orthogonal am of t and integrating over the time period t. So from this I can get the summation as c naught a naught t am of t plus c1 a1 of t am of t, so on and so forth, cm am of t into am of t plus so on and so forth, cn an of t into am of t. So from the orthogonal function we got to know that if n is equal to m, then only there is a constant k. Right? For the rest of the values it is 0. So this equation can be further simplified as integration x of t am of t dt is equal to k into cm. So cm is equal to 1 by k into integration t x of t am of t dt. Okay, so from this we can get to know the coefficients of the orthogonal functions, and an of t is the orthogonal functions. Now, this is a 1D equation, right? This is a 1D equation. So, similarly, we have considered till now an infinite number of samples, because x of t is represented by sigma n equal to 0 to infinity cn x of an of t, right? So, when we are transforming a signal into discrete signal, we have a limited number of samples. Right? So, we can represent the discrete function as a set of limited number of samples, which are n. So that can be represented by a vector u. Say suppose it can be represented by, which is summation of n equal to 0 to n minus 1 cn an of t. So this is the approximated vector which are representing by u cap, which is very approximated from by the discrete functions x of t. So C of n is the coefficient matrix, coefficients of the transform function. An of t is the transformation vector or basis function. So if I am considering discrete signals, then the set of samples are represented by u is equal to u of n, where the number of samples are n minus 1. Then if I am multiplying this set of the samples u with a unitary matrix A, then we get our transformed image. We get our transform vector. We call it as a transform vector. We call it as a transform vector. We call it as a transform matrix. Here we call this A as a unitary matrix. Here U is the set of the samples. So if I have a U, I am multiplying the U matrix by a unitary matrix A, then I get my transform vector. So I have U as my n samples. So my size of my U matrix is n cross n. I am multiplying my unitary matrix by n cross, or is of size n cross n. So my transform vector is also of size n cross n. Right? Now, if I want to get back my U, if I want to get back my set of discrete signals from my equation, then I will multiply the inverse of the unitary matrix on both sides. So we all know that if A is a unitary matrix, then A inverse is equal to A star transform, right? So I can represent it by A transpose star. V is equal to U, right? So this is one equation and this is another equation. So from this equation, if I want to represent this matrix form in equation form, mathematically in equation form, then I can say that V of k is equal to sigma n equal to 0 to n minus 1 a k comma n into u of n, where k is ranging from 0 to 1, so on, n minus 1, right? So from this matrix equation, I have represented the each value of my matrix V of k is equal to summation of n equal to 0 to n minus 1 a k comma n into u n. So here this is the set of samples. This is the set of samples where this is the unitary matrix or the unitary matrix or the basis function. Basis function. V is the transform vector. So similarly, from this equation, I have got my transform vector. So from this, which is represented by my matrix, I can get back my set of samples U. So how do I write my equation from there? It is very similar to the equation which we have dealt here. We can write U as U of n equal to sigma k equal to 0 to n minus 1 a conjugate k comma n v k, where n is ranging from 0, 1, 2, so on and so forth, n minus 1. Right. So this equation can be written as matrix equation can be written as U of n is equal to sigma k equal to n minus 1 a star k n v k, where n is ranging from 0, 1, 2, 3, so on n minus 1. So from this equation we can get to know that U of n, which is a set of samples, is represented by summation of set of orthogonal functions. So we have proved that if I have a set of sample functions, I can represent it in the form of summation of set of orthogonal functions. Sum of set of orthogonal functions. I've got my v, which is equal to a into u, and my u, which is equal to the a inverse of v, which is equal to the transform of complex conjugate transform v. So these two equations are very important for our image transformation techniques. So here we will consider few properties of A, which is the unitary matrix. And in other terms we can say it as a coefficient matrix. Right. So in our previous slide we have talked about the various types of image transformations, right? Various types of the image transforms, which are orthogonal and the other are non-sinusoidal, right? So if the A matrix is represented using sinusoidal functions, sine functions or cosine, then we call it as an orthogonal. So A matrix is represented using sine values. So A matrix values are calculated using sine functions. For example, if we consider F Fourier transform, then A is given by integration 0 to t x of t into sine omega t dt. So A of values are given by the A matrix values are given by 0 to t x of t sine omega t dt. When the other DFT term, if we consider, then the A matrix is given by the summation, double summation. If we are talking about a 2D dimensional, then m is equal to 0 to m minus 1, n is equal to n minus 1 x of t into e power minus j 2 pi omega t by n. So this exponential function can be represented by the combination of sine and cosine functions. So ft, Fourier transform, and dft can be termed as the orthogonal functions. When we come to non-sinusoidal signals, we have talked about Haar, Walsh, Hadamard, right? So there the A matrix is given by 1 minus, given by summation 1 minus power b of x into b n minus 1 by I of u. Okay, so my A matrix can be given by the summation of minus 1 bi of x into b of n minus 1 by x. So in detail we will see in our next class what is the Walsh-Hadamard equation, Haar transform, and how do we calculate our equations. So the property which I'll be talking about right now is the coefficient matrix is called as separable transform. Okay, I'm talking about the separable transform. I know that my vector u can be represented by summation. It's represented by the transform vector v is represented by summation k equal to 0 to n minus 1 a k comma n u n. This is a 1D equation. So if I want to write my 2D equation, vector equation, then v of k comma l is equal to double summation where k is equal to 0 to n minus 1, l is ranging from 0 to n minus 1, a k l m n into u of m comma n. So my 2D equation of my equation, vector equation v is equal to au can be given by this equation. Now I have my coefficient matrix as a k l m n. So this is a 2D function. A 2D function, if I am able to represent my 2D function, if I am able to represent my 2D function as multiplication of two 1D functions, then I can call it as a separable transform function. So I am representing my 2D coefficient matrix as a multiplication of two 1D matrices. Then I can call it as separable transform functions. So if I can talk in terms of this matrix, then a I have I have a k l m n. I can write it as, if I can write it as a k a1 k m into a2 function a. So if I'm able to write my coefficient matrix k l m n, which is of four variables, into two 1D functions, where 1D function k it is dependent upon each other k and m, l and m, then I can call it as separable functions. If the functions a1 and a2 are same, if the two functions are same, then I can call it as a symmetric, then I can call it as a symmetric separable transform functions. So the properties which we will be talking about in our image transformations are: A is the called as the coefficient matrix. A is called as the coefficient matrix, which is which satisfy which is also the unitary matrix, which is also the unitary matrix. They are If it is a 2D function, then I can say that it is a multiplication of two 1D functions. So it is a symmetrical function. It is a separable function. It is a separable functions. If these two 1D equations are same, then I can call it as a symmetrical equations. So all the FT transformation, Fourier transform function, DFT transform function, Haar transform, Walsh-Hadamard, and slant satisfy these three conditions, which is the coefficient matrix, they are the unitary matrix, they are the separable transform functions, as well as the symmetric transform functions.
Like, share and subscribe. Hit the bell icon for more updates.